Right, the next speaker is Adela DePavia, who's going to talk about leveraging adaptive algorithms, sensitivity to change of basis.
Cool. Sorry, 1 second. I'm a little short to be behind the podium. Okay. Hi, all. Okay, I'm excited to tell you about some of my recent projects studying adaptive algorithms and specifically their sensitivity to change of basis. This talk is based on work with some excellent collaborators, especially Vasilis, who'll be joining UW in the fall, Becca Willett at UChicago, and then some great master's students, Rick and Jose. So in this talk, I want to focus on optimization problems. So we're given some objective f that maps from RD to R, and our goal is to find some theta star that minimizes this function. So here I'm plotting the contours of some loss function that takes in arguments in R2 in the theta 1 and theta 2 axes. And what I want to talk about is small rotations to the loss landscape. So mathematically, we can always do this by defining tilde f, a map whose action is given by composing f and v for v an orthonormal matrix. Because v is orthonormal, this is very literally a rotation about the origin. We are not rescaling anything, and we preserve most of the important properties of this landscape. Okay. Despite the fact that this is seemingly such a benign transformation, I claim there is a family of algorithms whose performance can completely change under this kind of transformation. And moreover, this is an important family. Conservatively, I think it's probably been used in at least tens of millions of dollars worth of computation. So before I tell you what this family is, let me first prove my claim to you about their sensitivity. So here I've taken some mystery algorithm. I initialize it at the top right orange points, which are equivalent up to rotation. And then I run the algorithm with identical hyperparameters in both coordinate settings. And visually, we can see that the set of iterates produced is absolutely not equivalent up to rotation. Moreover, we've actually seen an impact on the rate of convergence. We're taking more iterations to converge in our first setting than in our second setting. Also, this is a convex landscape. But if this landscape were non-convex, then this kind of change could impact not just our rate of convergence, but also which local minimum we converge to. Okay, so the algorithms that exhibit this are the so-called adaptive optimization algorithms, and specifically here I'm running AdaGrad. But this is a huge family, so if you were guessing like Atom W, RMS prop, or basically any algorithm whose name starts with Ada, then I would give you full credit. So to explain what makes these algorithms so-called adaptive, I want to look at AdaGrad, which is, for me, a prototypical adaptive algorithm proposed by Ducci, Hassan, and Singer. So what AdaGrad does is it maintains what are called these adaptive coordinate-wise learning rates. So at time step t, it uses a learning rate, eta sub t for coordinate I, that's given by taking some base unchanging global learning rate and normalizing it by square root of some small stability parameter epsilon plus the sum over all of our previous iterates of the ith entry of the gradient squared. And what this basically allows AdaGrad to do is separately anneal the learning rates for each coordinate. So these kind of adaptive coordinate-wise learning rates are shared by all of the algorithms in this family up to small changes in how we define the averaging. And they all are the reason why these algorithms are sensitive to orthonormal reparametrization. So given this sensitivity, some natural research questions arise. First of all, can we understand what properties of an objective function would make these like algorithms more sensitive to change of basis? Like when will they be particularly sensitive? And then second, is this actually something we could exploit? So if you come to me with a loss function, can I give you a favorable basis such that if you reparameterize your function and then optimize in this new basis, maybe you can get even better performance? So that's what I'm going to focus on in this talk. Okay, so in pursuit of a favorable basis, we observed that if you read the original AdaGrad papers, they're heavily motivated by cases where the gradients are sparse or axis aligned. And what I mean by that is in this second right-hand figure, I'm plotting the direction of the gradient at different points in these red arrows. And you can see that at most points in the landscape, the gradient is nearly parallel to either the theta 1 or the theta 2 axis. Whereas like in this original coordinate settings, most of the gradients are either parallel to like 1, 1 or 1, negative 1. They're dense in this first coordinate setting. So given that the second framework is that kind of preferred by the ideal Adela formulation, can we find a systematic reparameterization that would rotate a loss landscape to make it more axis aligned? To do this, we propose EGOP reparameterization. So the EGOP matrix, or expected gradient outer product matrix of a function, is defined as the expectation over parameters theta of the gradient of f at theta outer producted with itself. And here this expectation is taken over a user-specified distribution. But for the sake of this talk, let's think about isotropic distributions, so like a Gaussian with covariance sigma squared times the identity. Okay, so the reason why we picked this object is because the eigenvectors of the EGOP matrix actually capture important principal directions of variation. So what I mean is, looking at this loss landscape, sorry it doesn't show up fantastic here. If we look at the leading EGOP eigenvector that I've plotted in red, you can see that it points in the one direction of the one-dimensional subspace where this function varies most sharply, whereas the trailing eigenvector identifies a direction in which the function varies more slowly. So the eigenbasis is an orthonormal matrix. If we reparameterize into this basis, what we see is that we actually get this kind of improved axis alignment property that we were chasing. So this suggests the following meta-algorithm. If you come to me with a loss function, we could sample a bunch of points theta, evaluate the gradient, use them to estimate the EGOP, take its eigenbasis, form tilde f, given by f composed with the eigenbasis, and then optimize tilde f to hopefully get better performance if you're committed to using like Atom or Adela. So it turns out that this meta-algorithm actually provably improves our convergence guarantees under some assumptions. So I want to focus on a setting where f is convex. We have some ball constraint set and a fixed step size eta. I'm going to, for the sake of time, not talk about all of my assumptions. I just want to highlight two. First, we'll have to assume that the Hessian is Lipschitz with a sufficiently small Lipschitz constant within our set. And then we'll assume that the original function is not extremely axis aligned. And under these assumptions, we can show that EGOP reparameterization improves the worst case convergence guarantees by a factor of up to 1 over d. So what I've got here is on top, I've got the convergence guarantee for EGOP reparameterized Adela, and down here I've got the convergence guarantee for Adela in original coordinates. And what really matters is that the only difference between these two bounds is the term that I've highlighted in yellow. So here we have something that looks like SRF divided by d, where d, again, is the dimension of our optimization problem. So for a high-dimensional problem, this factor of 1 over d could be substantial. This SRF is related to the stable rank of the EGOP matrix, and it's defined to be the sum of the square roots of the ith eigenvalues divided by the square root of the leading eigenvalue. If you squint at this, you'll notice that if the EGOP has strong spectral decay, then lambda I is very small compared to lambda 1 for most I and d. So this is going to be like some constant in those cases. It will not scale with d. And hence, we really do get a savings factor that's like constant over d. Okay, so we've shown that this EGOP spectral decay kind of mediates the sensitivity of these algorithms. And in particular, that when we have stronger spectral decay, our improvement guarantees are even better. I claim that this strong EGOP spectral decay is a super natural property in machine learning. So here what I'm plotting is the normalized eigenvalues of the EGOP matrix for some two-layer ReLU network function on handwritten digits. And if we look at this inset with the linear scale, we can see that the eigenvalues are decaying to 0 extremely quickly. So this is going to be a case when this stable rank is some small constant compared to d. And this is not the only kind of data set that will observe this. You can carry out this experiment yourself on your favorite benchmark. And it's also not like a property that comes out of the blue, like this kind of stable rank, small stable rank is related to the manifold hypothesis. So this suggests that we might expect improvement in a wide range of machine learning problems. Okay, so those were theoretical guarantees. How does it work in practice? Here I'm plotting training loss versus epoch for a bunch of different algorithms. In solid traces, I plot the performance in original coordinates. In dotted, the EGOP reparameterized performance. We see that the adaptive methods, namely AdaGrad and Atom, minimize training loss much more quickly under EGOP reparameterization. Whereas, like, I'll comment that like the baselines SGD and SGD with momentum, they basically don't change under reparameterization, and this is expected because they're actually rotationally equivariant. Okay. Some quick sanity checks. This improved minimization of training loss is leading to good performance on test accuracy. And these results are robust to learning rate. Like, you might have noticed that our guarantee held for any step size ADA. So I'm not playing a game of, like, pick the best ADA and different things and maybe you can get a gain. Okay. So in conclusion, what have we found? First of all, we've kind of raised this new hypothesis that this low-rank structure in machine learning objectives, quantified by the EGOP spectral decay, is what's mediating the sensitivity of these algorithms to change of basis. We propose this EGOP reparameterization to hopefully improve the performance of these algorithms. And then some ongoing work that I would be excited to talk to you about is actually investigating how the generalization of the solutions produced is itself sensitive to change of basis and what we can do there. So with that, thank you guys very much, and I'd be happy to answer questions. Yeah.
Presumably this has some, like, you had some conditional, like, distribution that you were...
Yeah. So I mentioned this, like, isotropic property. Those, like, mild conditions that I swept under the rug basically say, first, let's use an isotropic distribution, and then second, we need its scale to be sufficiently spread out. Exactly, yeah.
And then a related question, like, empirically, did you find, like, you could, in theory, you know, especially for non-convex problems, you could, like, redo the parameterization.
Yeah.
Don't you, like, think you, like, plateaued or something?
Yeah.
Did this help or anything?
So this is something I've only done a little bit. So far, I've seen that the upfront reparameterization is shockingly effective, so I'm not getting huge gains by doing it periodically. I think it, first of all, theoretically could definitely make sense. Like, you could cook up examples where you move to some new basin and reparameterizing would help a lot. But, you know, also maybe I just need to try out some more difficult problems empirically, and then I'll start to see that the periodic reparameterization buys me more. But yeah, I think that's a really natural thing to study. Thank you.